Hello everyone, my name is Qichu from School of Electronic and Information Engineering in Harbin Institute of Technology, Shenzhen. Now I will present our work Relative Intensity Noise of Injection-Locked Epitaxial Quantum Dot Laser on Silicon. This work is collaborated with telecom pairs in France. My presentation is divided into the following 5 parts. First is the context and motivation of our work. The relative intensity noise, abbreviated RIN, of the laser mainly stems from intrinsic optical phase and frequency fluctuations caused by spontaneous emission as well as the carrier noise, describing the fluctuations in the optical power of a laser. In future optical communication systems, optical sources with low RIN are highly desired to carry broadband data with low bit error rate. In laser technologies, noise mainly comes from the laser's RIN. The laser's fluctuations will be seen as a signal, so it will impact the detection range, resolution, sensitivity, and accuracy. The figure on the right shows the contribution of the different sources of noise to the maximum possible link output signal-to-noise ratio. With the increasing of the photocurrent, the intensity noise becomes the main source of the noise. This is very important in laser technologies. Therefore, in laser-related applications, it is also requested the laser's intensity noise to be drastically limited by the short noise. The picture on the top right shows the number of photonic components integrated on a single photonic integrated circuit over time for 3 photonic integration platforms. It can be seen that the integration level of monolithic and heterogeneous silicon photonics is growing rapidly and has exceeded the monolithic indium phosphide. Therefore, silicon-based PICs are developing rapidly because of their CMOS-compatible, low-cost, small footprint, high energy efficiency, and integration density. It has been considered as a mainstream data transmission solution for next-generation data centers, but there still exists some challenges, such as integrated lasers on silicon. RIN in silicon-based laser will impact the bit error rate and the dynamical properties, so we need to take some methods to search a laser that can be integrated on silicon with low RIN. Secondly, I would like to talk a bit about the merits of quantum dots. Due to the 3-dimension carrier confinement, quantum dots have high energy level separation. The discrete distribution of quantum dot materials makes it more tolerant to epitaxial growth defects and greatly reduces the influence of dislocation defects on the performance of lasers. We can see from the photoluminescence spectroscopy on the right that the intensity of silicon-based quantum dots is reduced relative to the native substrate, but the degree of the reduction is small, so epitaxial growth of quantum dots on silicon is a feasible solution. As I talked before, quantum dot systems exhibit an atom-like density of state, hence providing an ultimate carrier confinement. Thus, the quantum dots are advantageous for the laser devices, such as low power consumption, long device lifetime, thermal stability, integration cost advantage, enables smaller device, and reflection insensitivity. In the above table, we list some relevant research results of the RIN of quantum dot lasers. From the table, we can see, compared with quantum dot lasers on native substrate, the silicon-based quantum dot lasers have shown a bit higher RIN values of -140 dB per Hz to -150 dB per Hz. However, quantum dot lasers grown directly on germanium have higher RIN values, about -120 dB per Hz. Due to the lattice mismatch between the group 3 and 5 material and the silicon substrate, the epitaxial growth will produce a very high dislocation defect density, which acts as non-radiative recombination center through the SIH process and adversely affects the threshold current and noise characteristics of the quantum dot lasers. For this reason, the silicon-based quantum dot lasers have shown a bit higher Ring values than native quantum dot laser. The equation and the figure shows the relation between the non-radiative recombination lifetime and the defect density. Therefore, we use the method of optical injection to reduce the range of silicon-based quantum dot lasers. In this work, we established an optical injection-locked quantum dot laser model. Optical injection-locked semiconductor laser system involves two lasers, referred to the master and the sliver laser as shown in the left figure. Through optical injection, many properties of quantum dot lasers can be improved, such as improvement in modulation characteristics, controlled optical line width enhancement factor, suppression of frequency chirp and model hopping, reduce nonlinear distortion and relative intensity noise. By adjusting optical injection parameters, including injection ratio and frequency detuning, we can obtain the stable locked air, which is bounded by the Hopf bifurcation and the side node bifurcation, where the phase of the sliver laser is synchronized to that of the master laser. In stable locked air, the quantum dot laser exhibits improved performance. Therefore, under stable injection locked state, optical injection systems can be used for random bit generation, microwave generation, and low noise operation. The figure on the right shows the principle of the dynamics of the carriers according to the extonic model, which consists of a two-dimensional carrier reservoir as well as excited state and ground state of quantum dot. As shown in the figure, carriers are supposed to be directly injected from the contacts into the carrier reservoir. The dynamics of the carriers between the carrier reservoir and the states of the quantum dot are controlled by the different characteristic times, such as the realization time, the capture time, and the escape time. The differential rate equations describing carrier, photon, and phase dynamics are expressed on the left. In the equations, we take into account the non-radiative recombination lifetime tau SIH, optical injection terms, and the Langevin noise. The terms F respectively represent the carrier noise, simultaneous emission noise for the photon's number, and the phase noise. The modeling of the ring is done in two steps. Firstly, we transpose the system in the frequency domains. Then we introduce the Langevin noise, taking into account carrier's noise, simultaneous emission noise, and phase noise. The correlations between the two sources are defined as the equation, and the diffusion coefficients are expressed according to the following relationships. Finally, we use the small signal approach applied to the equations, and hence ring is defined by the ratio between the power spectral densities and the average of the power. Now I will present our simulation results. The relative intensity noise properties of the injection-locked quantum dot laser. As we can see, for the free-running laser, as the dislocation density increases, the laser's threshold current increases, and the low-frequency ring increases from -161.3 at tau SH equal to 10 nanoseconds up to -157.6 at tau SH equal to 0.5 nanoseconds. This confirms that the presence of the SIH process affects the noise characteristics of the laser. Then we add optical injection to the sliver laser. Here we analyze the effect of the injection ratio on the ring when the frequency detuning is 0. The left figure exhibits the ring of the injection-locked quantum dot laser at different injection ratios with tau SIH equal to 10 nanoseconds. We can see, as the injection ratio increases, the ring decreases in the whole spectral range, and the peak shifts towards a higher frequency along with a reduced peak amplitude. This variation rule is followed for different non-radiative recombination lifetimes. The right figure shows the injection ratio dependence of low-frequency ring at 0.01 GHz versus tau SRH. From the figure, we can see that the larger the dislocation density is, the more obvious the ring decreases after optical injection. The low-frequency ring is reduced by about 11 dB compared with the free running at tau SRH equal to 0.5 nanoseconds. In addition, when the injection ratio is large, the impact of defects can be completely offset, and the ring is almost constant. Based on the analysis of the time series of the photon number, the stable optical injection locked air corresponding to the ring can be obtained. The number of photons in the stable air will eventually tend to a certain constant, while the non-stable air is always fluctuating, as shown in the two pictures on the left. By extracting the injection parameters corresponding to the photon number in the stable air, the boundary of the stable injection locked air under different defect conditions is obtained as shown in the right figure. It can be seen from the figure that the SRH process hardly affects the stable locked air. This page displays the map of the ring with the variation of both injection ratio and frequency detuning at tau SRH equal to 10 nanoseconds and 0.5 nanoseconds. The ring in the stable injection locked air is reduced down to minus 168 dB per Hz with the increase of the injection ratio. It can also be confirmed that the SRH process doesn't affect the stable injection locked air. However, this stable air is asymmetric with respect to zero frequency detuning and shifts to positive frequency detuning. The asymmetry of boundary for stable air results from the asymmetry in the gain profile leading to a non-zero alpha factor. In order to express the influence of the alpha factor on the stable injection locked range, we analyzed the ring map and the different alpha factor values when the non-radiative recombination lifetime is 10 nanoseconds. Comparing these two images, it is obvious that the alpha factor changes the symmetry of the stable injection locked boundaries, and with the alpha factor increases, the stable injection locked air moves in the direction of large injection ratio and frequency detuning. Finally, I will summarize the conclusions of our work. For the conclusion, the ring of laser is enhanced at shorter non-radiative recombination lifetime, whereas high ring characteristics is suppressed by the optical injection. The larger the dislocation density is, the more obvious the ring decreases after optical injection. When the injection ratio is large, the impact of defects can be completely offset, and the ring is almost constant. SRH has little impact on the stable injection locked air. In the stable locked air, the ring is reduced down to minus 168 dB per Hz by adjusting the injection ratio and the frequency detuning. In the future, we will continue our research from the following two parts: the phase noise properties and the modulation characteristic under optical injection, comparing the results of experiments with numerical simulations. That's all. Thanks for listening.